Okay, that means let's start. This is week, I believe this is week 12, and we're starting a new chapter and the new part of calculus, which we will call integral calculus. Okay? That means let's see. And I will just cover the first section, 4.1, because it's chapter 4. That means what we had. So far, we talked about some tangent line problem or the velocity problem, and everything was introduced, of course, through the derivative. That means we know what is derivative, the central idea of differential calculus, of course. Okay? That means what we will do in the same way, we will start this chapter, and the same way, I mean, we will try to approximate something. Like probably you remember the introduction to derivatives, we were trying to like approximate the slope of the tangent line, because we still know that we can't really take the slope of the point at the point and itself, because we will have no rise, no run, 0 over 0, but we know the magic tricks to deal with the fraction 0 over 0. Okay. That means now we have a little bit different problems. We have like the area problems and the distance, but we will mainly focus on, can I write? Area problems. Okay. And we will try to define, we will try to formulate this. And we will, of course, get some definition, important new terminology, and this will be the integral, a definite integral. And this is the main concept of the second part of calculus, which is the integration calculus. Okay? We will also have in this chapter, not in this section, not in this session, but in the chapter 4, we will have something that is connecting integration and differentiation. Okay, we will see what integration means, of course, and we will see how integration relates to differentiation, and then we will formulate a fundamental theorem of calculus. And that means this is like a circle, like we will connect everything. Which I can say that the integrals were kind of introduced last week. Finishing chapter 3 with anti-derivatives, yeah, it will be almost the anti-differentiation. It's the process of integration. We're still not naming like integrals, we're still not using that terminology, notation, labels, but it will be almost the same thing. Okay, that's when I shouldn't tell you this, but because we have to introduce nicely, slowly, step by step, but that's what it is. Yeah? Anti-differentiation, it's simply an integration. That means having a function, we know how to find the derivative. But now, having a derivative, the rate of change, we would like to recover an original function. And that's anti-differentiation, but also this is called integration. Okay, but let's start, as I said, slowly, and let's start with just the areas problem. Okay? Like how can we find the area? And especially, and keep moving, I will switch off the video in a minute, especially the area under the curve. Okay, that's when we can see we will have a little bit of challenge. That's what we have. First of all, we definitely like have the feeling like what is the meaning of the word area. We know how to find the areas of some shapes, right? Especially if the shape has all of the sides straight. That means, let's see. Rectangles, we all know the area, we have to like hug everything together, length times width. Triangles, yeah, a little bit different, but we also know the formula, 1/2 base times height, easy. And maybe something fancy, polygons, right? Doesn't really matter what shape we have, we can always create triangles, maybe rectangles, but in this case it's easy to have the triangles. And having all of the triangles, we can find the base, the height, we can add them together, right? That means it's not a problem. That means the problem starts if one of the sides, or maybe more, are not a straight line. That means let's see something like that. Okay. We do have a function. I will switch off. Okay. That means we have a function f of x. Okay, f of x. And this is function. And at the moment, the function f of x is just above the x-axis, positive. Yeah, because we don't want to involve the negatives at the moment, of course. That's when we have nice function. We will restrict the domain for now from A to B only. And we will highlight the region under the curve and above the x-axis and between the vertical lines A and B. That we do have the region S. And we would like to find the area of this. And we can see it's nice straight bottom, nice straight lines as a side, but the top is like too wavy. Okay, that means I don't know. I can't really say this is a rectangle. I can't really say it's a triangle, or maybe trapezoid. No. It's not the shape that we know, right? It's not the shape. It's not a nice straight shape. That means I have to use some tools to, first of all, to approximate that area. Even if I will do something like that, even if I will find the area of the rectangle, right, it's not a perfect approximation, but at least I have some idea that the area of my region will be less, and I would say much less than the area of this rectangle. And I can easily find the distance between A and B, right? That means I can even write now, because this will be big thing. The distance between B and A and B is simply B minus A. Yeah, the distance of the whole interval, that everything is defined. And then this, because we know that the area of the rectangle is base times height. Okay? That means this is my base, and height in this case will be simply the value of the function for the endpoint A, the beginning A, f of A. That means this B minus A times f of A. Okay? Easy, but of course it's not a perfect. Let's make a little bit better approximation. That means what we will do, okay, I have a few notes. We can pause for a second and we can read this. That means, as I said, we will try to like make some approximations, some intuitive ideas, similar to find that area, which I actually did something, right? I did kind of like through the rectangle. We also, that's what I wanted to mention, we remember the tangent line. We were also approximating using, of course, the slope of the secant line, and then getting the secant line, we're getting closer and closer and closer to the tangent point of the tangency, and almost like the secant line almost reminds us the tangent, and then we finally got a slope. Okay, that we will do something, I mean, of course, different thing, but the same base, the same idea. We will approximate. Okay, and let's see what we will do. We can take a more specific area because we know the function. That means we will still come back to the original question, but we didn't know the formula of the function. That means let's look at this example. We have to estimate the area under the parabola x squared. That means this is parabola x squared. We know how parabola looks like, from 0 to 1. That means from 0 to 1. I did cut. Okay? That we can see. Yeah, in this case will be not really helpful if I will make that. I can still get that area, the big rectangle, or I would even say it's a square in this case, but my area is even less than the half of this. Yeah? Still I can approximate. But what we will do, I keep like building one big rectangle. We will try to use the same idea, but we will try to create more rectangles. Right? And in this case, we will use 4. Yeah? We always have to like make sure what number is given. That means what I did. I took an interval between 0 and 1, that's what was given, and I divided by 4 equal sub-intervals. That means 1, because the distance between 0 and 1, it's 1, dividing by 4, right? I can even say b minus a, which is 1 minus 0. Of course, it's obvious, it's 1. We don't even have to do the math, okay? That means we know that the distance is 1. Just the formula if some numbers are maybe more complicated. That means the distance is 1, and what I did, I took that 1, okay, and I divided by n, which in this case is 4, 1/4. That means the length of or width of each sub-interval, it's 1/4. 1 divided by 4, 1/4. Another 1/4 is giving me half, another 1/4 is giving me 3/4, and 4/4, of course, is the whole 1. Okay. And then I'm creating these lines. Okay, that means I'm trying to create, first of all, like 4 strips. Okay, we have 1, 2, 3, 4 strips. But you probably know what I'm gonna do. I'm gonna create a rectangles because I know the area of the rectangle. And now we have thousands of different ways to create a rectangle, because what I need to get the rectangle, of course, I need the base. This is base, which I do have my base, 1/4 for each of them, okay? And I need a height. I need a height. Base times height, of course, is the area. That means now it's important, yes, when you're watching this, it's really important to know how I can create my rectangles, because I need the top to be the straight line. Okay, let's take the first sub-interval. The first sub-interval is between 0 and 1/4, okay? And we will focus only at the moment on 2 ways to get the rectangles, okay? As I said, we have multiple ways, but we will focus on 2 for now. That means how can I get my rectangle? Again, looking at the sub-interval between 0 and 1/4, I can see 0 and I can see 1/4 as the endpoints. One of them we will call the left-hand side endpoint, and the other one, of course, respectively, is the right-hand side endpoint, okay? And in this case, we can pick one of them. We can pick left or right. I will pick right for now. That means 1/4 is on the right-hand side, and I am picking the right-hand side endpoints to be my sample point to create my height. That means the value for 1/4, which is this, will give me the height. And I will build my first rectangle. Of course, this is the value of the function for 1/4. This will be the height. Okay, now let's jump to the second sub-interval, second strip. Okay, 1/4 and 1/2, right? Again, looking at both of them, 1/2 is on the right-hand side. That means 1/2, that corresponding value will give me the height. And I'm building my rectangle. And this is, of course, the height will be the value for 1/2. I don't have enough room, but actually I did squeeze it. Okay, and I will repeat the process for the 2 remaining strips. 1/2 and 3/4, that's my next sub-interval. 3/4 is on the right-hand side. That means I'm looking for the value, that's the value, and this level, this line will give me the height. That means this is the value for 3/4, and that's my rectangle. Okay, and then 3/4 and 1, 1 is on the right-hand side, and this will give me the height, value of the function for 1, which of course is 1, and I have to add this. Okay, that we can nicely see it's, again, not perfect, because adding the areas of all of these rectangles, I think I'm adding a little bit too much than my original region, but I can still approximate. That means, let's see, I do have an extra slide for this. That's my right-hand side endpoints. Okay, and then each of them, I can still repeat, this will be half. This is the value for 1, actually the other way. 1/4, 1/2, value for 3/4, and value for 1. Okay, that means in order to get all of the areas, I will add the first one, second one, third one, and the fourth one, rectangle. Each of them has the base 1/4, okay, 1/4, or the width of the rectangle 1/4, and then the first one has the height value of the function for 1/4. Now the second one, base times height, 1/4, and the height is the value of the function for 1/2. And then the third one, it's 1/4 times the value of the function for 3/4. Okay, and the last one, it's 1/4, and the height was the right-hand side point 1. Okay, that means adding all of these, I can get the approximation. That means, let's see, of course, value of the function for 1/4 is the 1/4 squared, because function is x squared. Value of the function for 1/2, it's 1/2 squared, 3/4 squared, and 1 squared. That's the values of the function. And then I use I think I used calculator just for this one. This was not bad. I square the numbers, multiply by 1/4, common denominator, add them together. I've got 15/32. We can see almost half. Almost half. A little bit less than half, right? Okay. But we can see our rectangles, this is the area of the rectangles. That means we definitely overestimated, because the rectangles are sticking out, right? They not really cover perfectly my region, okay? But it's at least a number, okay? It's at least some approximation. We will try to make it perfect. We will try to fix it. Okay, and as I said, we did use the right endpoints. We can repeat the same process, and we can use the left-hand side endpoints. That means, let's see what we will have. Actually, let me come back for now, because I have the picture. Let me come back for this one, for this picture. Okay, I will just use this one to use the left-hand side. That means, let's go quickly. From 0 to 1/4, that's my first sub-interval, and 0 is on the left-hand side. That means 0 actually has the value 0. That means it's nothing. It's just the line. It's just the 0. No rectangles. But that's how how end up having the height 0. Okay, let's using the left-hand side points. 1/4 and 1/2. Right? That's my second sub-interval. 1/4 is on the left-hand side. That means 1/4 will give me the height. 1/4 times the value of 1/4. That's the area of the second rectangle. That's the second. 0 is the first one. Okay, the third one has 1/2 and 3/4. 1/2 is on the left-hand side, and the corresponding value, the corresponding horizontal line, will give me the height. That's the third one. And 3/4 and 1. 3/4 is on the left-hand side. This value is giving me the height for the fourth one. That means this one we can see when we add all of them together, the rectangles, the areas, we will definitely underestimate, because we have some region that is not covered. Okay, let's see. I have the picture for you. Left. Okay. That means this is the left-hand side. Yes, we remember the value for 0, okay? Value for 1/4 will give me the second height. Value for 1/2 will give me the third one, and the fourth one, value for 3/4. Okay? And then adding, again, squaring them, because the function is x squared. adding common denominator, we're getting 7 over 32.2. Okay, that means we know definitely that we underestimate, and we can, so far, we can say this, that the area under the curve is between 0.2 and 0.4, 0.2, 0.5. Okay. It's not bad, but we did quite good. We got quite good numbers. Okay, but as I said, we're gonna fix this, and you can probably notice that the problem is the number n, the number of rectangles. That's actually not enough. I can definitely improve my approximation if the number of rectangles is actually bigger. And let's see. Yeah? The number of strips. That means even if I will use 8 of them, let's look at this. Of course, I will go by 1/8, 2/8, 3/8, and so on, because I'm dividing 1 by 8. Okay, that's my left, and that's my right-hand side. And I think I used the same method, but I'm not gonna bore you. Okay, this is underestimation, 0.27. This is overestimation, 0.394. We can see we're getting a little bit better numbers. And I just doubled the numbers. But you can probably notice that if I will get extremely big numbers of rectangles, of strips, the approximation will be almost perfect. Let's look at this. 10 rectangles, 30, 50, because as soon as I make the base of the rectangle, the width of the strip, I can almost perfectly fit the line, if they are like really, really tiny. That means even with 50, yes, we're getting, and we can see that's the right-hand side endpoints, that's the left-hand side endpoints. Yeah, they are a little bit lower, a little bit up. And using the right-hand side, 10, we have 0.38, 0.35, 0.34. Okay, this is 32, this is 31, 28. That we can see we probably getting closer and closer to 0.3. Yeah, but I'm just guessing. That we can see, and this is only 50. You can probably guess, since calculus involves the teeny tiny numbers, or also the other extreme, calculus involves the big numbers, infinity. That means we can probably guess that if number of strips is infinity, if we have infinitely many of them, then it's just the area under the curve. It's just these rectangles will cover exactly the region under the curve. Okay? That means the perfect thing is to have n being infinity. Okay? Of course, I don't know if we can imagine, this almost looks like infinity many of them. And if infinity is involved, something like that, of course, the limit will be involved. We have to approximate our formulas, how the formulas behaves as n is infinity. And I do have the numbers, just the numerical values for you. This is number of the strips or rectangles, 10, 20, 30, 50, 100, 1,000, and we can see just 1,000. Left-hand side and the right-hand side endpoints. Yeah, they almost the same. That means, of course, the point is to get infinity. And that's what I said. I'm guessing that this is like 1.3, 1/3. Okay, and that's what I would like to say, that we know what this means. I did have on the previous. This means that this is the areas of all of the rectangles using the right-hand side endpoints. We may have the same thing on the left-hand side endpoints. And let's get the formulas. Okay, that means now, again, getting back to our example number 1, we don't have the formula for f of x, but we will just develop some formulas here. That means, let's see what we will need. We will need, first of all, we have to divide, okay, by sub-intervals, by n strips, and of course n is infinity. That's equally, okay? That means the interval from A to B is divided equally by n. Let's see, that means that's something like this. The first one, S sub 1, S sub 2, 3, and then we do have infinitely many of them, and then the last one will be S sub n. Okay? And n, of course, is changing, or I can say I is changing from 0, or actually 1 to n. Okay, that means we can see we have infinitely many of them. That's the indication. Okay, now we have to know, I did this, how to get this value, the width, which we will call delta x. Okay? And we know that delta x, it's simply the entire interval from A to B dividing by n. Yes, we did write this. That means that's important. Okay, now, okay, that's the width of the entire interval, b minus a. Okay, now the width of each n strips is, that's what I put it down, b minus a, okay, the distance from A to B, and dividing by n. If n is 5, we will divide by 5. If n is 100, we will divide by 100. But if n is infinity, we have to keep n, and then simplify. Okay, now each sub-intervals, that's actually the endpoints of the sub-intervals. X sub 0, x sub 1, x sub 1, x sub 2, and so on. Okay? And of course, this is the beginning, and that's the end. Okay, now what I also will do, because what will be normally given? We will always have A and B. That's not a problem. We will have, of course, the formula of the function, okay? But we will have A and B. And now we remember picking the left or the right-hand side. Okay? We have to find the height of my rectangle. That means, let's say, the right endpoint. That means this will be the height, and that's my rectangle. Oh, a little bit. That's my rectangle. Okay? X sub 2 is on the right-hand side of the next one. That's my rectangle. And again, that's my rectangle. That's my rectangle. And so on. I don't want to mess up. That's on the right-hand side. That's on the right-hand side. That means I have to really know what is the value of these sample points, x sub 1, x sub 2, because if n is infinity, I have to have like general formula. That means what we will try? We will try to find the formula for the sample point. Okay, sample point is like this one, x sub 1, x sub 2, 3, and so on. And that's what I just said, that we do have lots of ways to get the sample points. We focus only on the left and the right, but for this formula, we only limiting to the right-hand side endpoints. That means, let's see. Okay, I do have type, but I want to explain first. That means I know my A value, definitely. And that means the first point, x sub 1, it's definitely just delta x away from A. That means I can say A plus delta x, because if this is A, I'm adding delta x unit, and I will have delta x. I can compute it. And then I will jump to x sub 1. Then x sub 2 actually is 2 times delta x units away. That means I can say that this is x sub 1. X sub 2 will be A plus 2 times delta x. And then I'm here. And then again, x sub 3, x sub 3 will be 3 delta x away. That means A plus 3 times delta x. And that's what I have. Yeah, let's see, I do have this. And of course, x sub n will be n times delta x units away from A. That means this, actually, I shouldn't box this. This is important formula. Okay, that's really important. That we know we know how to, I can use maybe different color. We know how to get the length of the entire interval, b minus a. Okay? We know how to get the width, length width, I'm just trying, yeah, the base of each sub-interval, we will call delta x, b minus a over n, okay? And also we have to know how to define the sample points, x sub n, using the right endpoints. Okay? And we will not get the formula for the left endpoints. We can use the left hand side points if n is the finite number, but not if it's infinity. We will deal with the right endpoints only. Okay, that we do have three blue boxes. Make sure that you remember these formulas. Okay, this one, and this one. Okay, and let's see. Okay, I do have more. That means now let's get more formulas, because we know always when it's the introduction to a chapter, it's more theoretical part. Okay, we will still compute something today, which actually we did. We did the approximation under the x squared, but this is mainly like the focusing on theory. Okay, that's what we have. It's still the same thing. And adding all of these rectangles, okay, the areas, let me see, the areas is just delta x. I can write one more time, okay, delta x, and times the value for the sample point. That means sample point we will call x sub I, okay, like the ith rectangle. And we can see that's the area of one rectangle. Delta x, which is the base, times the height, okay, base times the height, and height is the value, the corresponding value for the sample point of the function, f of x sub a. I can just say, oh, actually I do have, wow, I do have nice indication of this. This is actually the height times the base. Okay. And now this is only one rectangle. If I would like to approximate the area, I will add all of them. And we can see the value of the function for x sub 1 times delta x. That's still the area of the rectangle. The first one, the second one, and the nth one, using the right endpoints. Okay, that means this is the approximation of the area of the whole region using the right-hand side endpoints. And what we have? We do have the addition of almost the same terms, like the value of the function for the first point times delta x, value of the function for the second point times delta x. That means we do have something like, how can I say, the sigma notation. And the sigma notation, it's used when we adding a similar terms, because sigma means addition. Right? That means what we can do, I have on the other side, but addition, okay, means sigma, that's addition, okay? And what we adding? We simply adding f of x sub I times delta x. And I, its number of these rectangles, is changing from the first one to the nth one. Below, the index below is telling me what we're starting with. And we can see x sub 1, x sub 2, x sub 3. And then on the top, it's telling me that I have to end at n. And always n are the counting numbers, natural numbers. 1, 2, 3, and so on. Positive integers. Yeah? We do go by positive integers. Okay, that means sigma notation. Instead of like writing all of them, we can just use sigma. Okay, and let's see. Oh, and this is of course the finite number, 2 rectangles, 4, 8, 12, and so on. And of course, if it's infinitely many of them, it's worth to use the sigma notation, because I'm not gonna like have the expanded form for, I don't know, 120 terms, for example. Okay, that means now, hang on, we know that if it's infinitely many of them, it's the perfect approximation. That means now having this, we know what this means. One rectangle and the area of one rectangle, the area of the second one, and so on. And I want this n to be infinity. That means I'm simply looking at this and computing a limit. Limit means the approximation of the formula at infinity. Okay? Like how this expression will behave if n is huge. Of course, algebraically, because we know what graphically means, perfect approximation. And this is just the left endpoints. We can see for the left, we're starting from x sub 0, and we will end 1 point before, because that's on the left-hand side. Okay, but that's how we can incorporate the limit definition. Okay, let's see. Now I will use sigma notation, but I have one more information for you. As I mentioned a few times, we may have also different like sample points. One more time, we're only focusing on the left and the right hand side points. If n is finite number, if n is infinity, only on the right hand side points. But let's look at this. We may have any sample points. Yeah? Instead of using just left or the right, like let's look at this one. Some of the mathematicians, they will say, because they will try to fit perfectly, like what is the optimal value of x that will give me good height, good rectangle. Because they want the rectangles not like, they will stick out anyway, but they want to stick as small as possible, like areas. That we can see, it's this point, this one looks like the middle one, this one looks like this one. Yeah, that we can see. We may have random points. Depends what it's less predictable, and we will have a little bit, like it will be time consuming to really find this value of x and then find the corresponding y value. Okay? But I have to tell you that we may have any sample points. That means if you will see this little star like asterisk, we will say, oh, that's like just different sample point. Okay, like that's, but the same idea. Height times base, adding all of them together, infinitely many of them. Perfect approximation. Okay, but please note that we do have different sample points than the left and the right. The left and the right are the easiest one. Or even the right is, for the infinity, it's the easiest. Okay. And now sigma notation. That's what I just said. Okay, I can show you the whole slide. Okay. That we can see that's sigma. The Greek letter, of course, everybody knows sigma. And sigma is telling me that I have to add. That's when I'm adding. What I'm adding? This. Height of the function, height of the rectangle times the base. The base is not changing. That means delta x will not change for each term, but f of x sub I will change. X sub 1, x sub 2, and so on. And we can see why I'm starting from 1 and why I'm ending at n, because that's what sigma is telling me. This is telling me to start with 1, and this is telling me to end with n. And by counting numbers. Okay? That means make sure that you know the sigma notation. And then I just write, and you can probably guess this is the right endpoints. Okay, actually the limit using the right-hand side endpoints, the areas, and this is one less, that means this is the left endpoints. But as I said, we will mainly focus on the right if n is infinity. And this is just sample points, right? I can maybe say, no, I don't want to say s because that's not a typical labeling, but we can see we can have any point. That means now remember that's also important formula for today. Limit of the sum of all of the rectangles. Of course, limit means the n is infinity. That means summation, the addition of all of the areas of the rectangles will give me good approximation of the area under the curve. Okay, well, too much formulas. And now I do have some just for the sigma, like let's say something like that, just I. This is just maybe 2-3 minutes like exercise for the sigma notation, to play with the sigma. This means that I is changing from 1 to n, and sigma is telling me to add. That means it's just addition of the natural numbers. 1 plus 2 plus 3 plus 4 plus 5 and so on, and up to n. If this will be, let's say, 100, okay, it's 100. You can probably keep adding them and get the number, right? Or if it's 1,000, it's 1,000. If it's infinity, it's like that, it's infinity. Okay? And I don't know if we remember from the pre-calculus, the algebra class, we do have a formula actually for this, and looks like this. If you would like to add, as I said, like 100 numbers, you don't have to sit and add them together, 1 plus 2 plus 3 plus and so on. You can use this formula. You can substitute 100 times 101 over 2, okay? Which I think it's, can we multiply? 101 times 100, it's 2 zeros, and dividing by 2 will be 5, and 5,050. Okay, because I can divide this by 2 and I can divide 100 by 2. Okay, I mean, we don't really have to know that, but I'm just trying to show you how we can use the formula. Okay, as we can see, we do have the formula for addition of just counting numbers. We also have something, I do have the proof, but I can show you the proof, like how we actually end up with this formula. Okay, of course, it's the whole story. We did have the mathematician Gauss, Carl Friedrich Gauss, and when he was like, of course, the school boy, he kind of like developed this formula. That's been what he did. Because the teacher, of course, asked to add numbers from 1 to, and I think was 100. That's what the story is telling. And she thought that, everybody will now sitting and adding. That's when I do have time. But then suddenly, one boy raised the hand and he gave the number, which actually was 5,050. And she said, wow, can you explain how you did it? Of course, he was the genius. That's what he did. He took all of the numbers from 1 to 100. Okay. Now he took the same numbers, but with the reverse order. 100, 99, 98, and so on. And then he added them together. 1 plus 100, 101. 2 plus 99, 101. 3 plus 98, of course, 101. That we can see we do have 101. How many times? 100 times. We have 101 100 times. That means if I will multiply 101 times 100, I am getting that number, but this sum is actually double, because we can see I double my hundreds. That means I have to divide by 2. 5,050. Okay? That we can see that's how the formula was created. Having 100 numbers, 100 is my n. That means n times n plus 1 over 2, because I don't want to have double sum. I have to divide. Okay, that's just the little story. Of course, would be nice if you will remember this formula. You don't have to remember the proof, but it's nice story. Okay, we also have another formula. I did type this. Excellent. Okay, that means this is actually that. Okay, I do have, that means we know this formula. I also have the formula for addition of the square of the counting numbers. 1 squared plus 2 squared plus 3 squared and so on. And this formula, we also have a formula. This one looks like that. And I can tell you we don't have nice and easy proof for this. We do have the proof. You can check the textbook, but it's way complicated. And we also have cubes. 1 cube, 2 cubes, 3 cubes, and adding. Formula looks like this one. And this one is also way complicated, too complicated to prove it. but the proofs exist. Okay, that means that's just like the addition of numbers, and addition of the squares, addition of the cubes of the counting numbers. And that's the formulas, which they are helpful because we can, as soon as we see this, we can rewrite these formulas, right? I mean, we can see infinitely many terms we can like replace by rational function, I can say, or polynomials, because it's the constant in the denominator. Okay. And I also have, okay, that's just the summary of these formulas. And let's actually do one exercise and we will be done. Oh, okay, that means just to know how we can replace. Also, a little bit of property of the sigma notation. If we have constant, we can always put the constant in front. Yeah, it's not really I mean, we have to multiply, but it's not affecting the main formula. If we have the sigma of addition, it's simply addition of two sigmas, sigma of the difference of two sigmas. Summation, of course. Okay, and then we can try, I mean, you can try to compute this. You can try if you can get these numbers. Okay, that's, we can see what I did. If we have summation of k squared, and actually this should be k. K is changing from 1 to 5. This means that I have to take 1 squared plus 2 squared, 3 squared, 4, 5 squared, and add them together. This one is, I'm trying to k. Now, please note, we have the formula 1 over k, and k is changing from 3 to 5. 3, 4, 5 only. Okay? And then now, k. K is changing from 1 to 19, from 1 to 19. And for this one, I could sit and add them together, but I did use the formula because it's the counting numbers. 19 times one number more over 2, n times n plus 1 over 2. Okay? And then something like that, because we always confused, if we have just the constant. This means that I have to add 2 plus 2 plus 2 plus 2 6 times, from 1 to 6. 1, 2, 3, 4, 5, 6. Okay? Of course, I can write right away 12. Yeah? That means we're actually adding, we're not changing each term. It's just constant. Okay, that means just to be confident with the sigma notation. Okay, and now, as I said, I do have one problem. Let's finish this session with this question and we will be done. That means we approximate the area under the curve x squared, but only from 0 to 1. Now, I would like to expand an interval from 0 to 4. That's what we have. Estimate the area under the graph x squared using approximating 4 rectangles and the right endpoints. That's what you can see. I did use the right endpoints to get the height. And it's simply 1, because distance from 0 to 4, it's 4. Dividing by 4, it's of course 1. That's why I'm going by 1. 1, 2, 3, 4. 1 is the base of the rectangle. 1 times the value of the function for 1. 1 times the value for 2. 1 times the value for 3, and so on. That's what I'm doing. I'm trying to use my sigma notation, even if we have only 4 rectangles. That means I will be adding all of the areas of the rectangles. Delta x, of course, is the base. And we know that it's 1 in this case, okay, because it's 4 minus 0 over 4. It is 1. Okay, and we're adding 4 of them from 1 to 4. Each of them still should have a delta x because it's constant, but since delta x is 1, I'm kind of ignoring. And x sub 1 is 1, x sub 2 is 2, 3, 4. The value of 1, it's 1 squared. The value for 2 is 2 squared, and so on. Let me write, because I don't want to ignore, not always delta x is 1. That means remember to have this number. Okay, and then I add all of them, I have 30. That means the area, the approximation with this scenario is 30. And let's do the left endpoints. Okay, the same thing, but the sigma is a little bit different because we're starting from 0, 1, 2, 3. That's the height, that's the height. So we can see we always end up with 1 less. The value for 0, for 1, for 2. As we know. Of course, if it's so little, the number of rectangles is 4, we can skip the sigma notation. I'm just trying to show you how we can deal with this. Okay, that means this is 14. Oh, that we can say that that area is between 14 and 30. It's a huge, right? It's not a perfect approximation, but we just learn, we know why. That's not enough, right? But make sure that you know how to find the area under the curve, how to estimate the area under the curve, having number of rectangles and the interval and the function. Okay, and then I just have, we know, I mean, this one is the original question from 0 to 1, and we know that it's 1/3. And actually, I would like to show you the proof of this, okay? Because what we know, let's see this. Oh, actually, I can, hang on. Let me just, okay, I will, because I type it, but I would like, no, I can show you here. I wanted to retype. Because what we have infinitely many of these rectangles, we can see. Each of the delta x will be the whole interval 1 divided by n, 1/n. That we do have this. Each of the height, using the right endpoints, of course, right, it's 1/n. 2/n, because this will be 2/n. This will be 3/n. To the power of 2, because that's actually this x² function. Okay. So now let's see. We do have delta x and the value of the function for the first point. And then again, delta x and the value of the function for x sub 2. And so on. Delta x, value of the function for the third point, and the end. That means let's try to evaluate this, because we know some formulas. 1/n, 1/n, and 1/n, it's a constant, right? That means I'm taking this outside. Also, we can see that I have 1/n squared, 2/n squared, 3/n squared, and so on. That means each of this number has a denominator n, and it will be squared, then I can factor out 1/n squared. And what stays? Only the numerator, 1 squared, 2 squared, 3 squared, and so on. And then multiplying these two together, this is my delta x. I have 1/n cubed, and I have addition of the square of the counting numbers. And we remember this formula, and I can simply replace. That means this one is equivalent to this. Okay? And I think I cancel out that n and that cube, which is squared. And now we can see I have to take this formula. Oh, actually, I did copy this one, which I can still cancel out. And I have to find the limit at infinity, because that's how I can investigate the behavior of this. And I have n and 2n, which will give me 2n squared, and I have 6n squared. Because limits at infinity, we only focus on the leading function. The leading functions are the same. The ratio of the leading coefficients, it's 2/6. It's 1/3. That's we can see how nicely using some formulas we actually get the exact value of the area under the function x squared. Squared we can see. Yeah, it's just nice steps. Okay, but as I can, maybe I don't want to scare you. Everything is important in this session, but make sure that you know how to get this approximation if n is a finite number. Like let's say, can I come back? Like let's say 4. Okay, like how to add all of them together. We don't have to employ the formula and so on. Okay, but it's worth to know how we got 1/3. Perfect. And this is the moment that we actually using this formula. Oh, I'm trying to do this and this. Okay, and then that means what we did, we really focus on something like this, okay, today. And we only use this for getting the area under the curve, okay? But I can tell you that this limit of the summation, okay, of these things, it's widely used in like in science, in engineering, in business. That's all we can see. I type few like application of this, okay, limit of the sum. Distance traveled, which we will not, we will not talk about these applications, but I can tell you that the same limit is applied. Distance traveled, length of the curve, volumes of the solids. Actually, volumes of the solids, we will talk about this. Centers of the mass, we will not talk about this. Force due to water pressure, work. That means all of them, if we would like to define this, we will use this limit of the sum, and we know what this means. Kind of like a base times height. Yeah? We like approximating. And since this limit of the sum has lots of application, we need a special name and special notation. And I can tell you that this is, as always, like we need a name and a notation. And the name is a definite integral, which of course I will stop there, and tomorrow's session will cover section 4.2. That means definite integral, I can say for now I still not giving you the notation. And do I have enough room? Limit of the summation from 1 to n is infinity, the height times the base. Okay? That means this is something like that. That means for now, you just know the definition of the definite integral. And tomorrow, Dr. Bank, he will explain this further. But make sure that you know all of these formulas. And I can even write for you, you have to know delta x. Okay. Of course, we know what is b minus a, and you have to know the sample point. A plus n times delta x. That means that's the main thing from today. And you're ready to attend the next session. Okay, thank you very much, and you will hear from me next week. Of course, any question, please post on the discussion board and do all of the suggested homework problems.